In this chapter, I will discuss gravitation, and more specifically the gravitational force that arises between objects. Now, since this is a specific type of force, of course it will have its own specifics due to the nature of how it is created. However, the fact that this is a force implies that all the knowledge that we have before for how forces act, superposition of forces, and so on and so forth, will apply for the gravitational force as well. The gravitational force is one of the fundamental forces in nature. The gravitational force is responsible for us being able to stand on the surface of the Earth. It is also responsible for the Moon orbiting around the Earth, and of course for the Earth orbiting around the Sun. The gravitational force holds the Sun together with the stars in our galaxy, the Milky Way. And the gravitational force is far more reaching than that, because the Milky Way and several other galaxies are held together by it in what is known as the local group of galaxies. The local group of galaxies is part of the local supercluster of galaxies. All of that being held together again by the gravitational force. And then the local supercluster of galaxies is being pulled towards what is known as the Great Attractor, which is a region in the universe that is extremely massive. Just for reference, the Great Attractor is about 3 times 10 to the 8 light years away from the Earth. However, this is not the range of action of the gravitational force. The gravitational force permeates the entire universe. It holds everything together, and we know that the universe is expanding. The gravitational force is also responsible for black holes. Black holes are objects created by the collapse of heavy stars when they are at the end of their lives. Black holes exhibit extremely strong gravitational forces, and so objects that end up close enough to a black hole never can escape the gravitational pull from that black hole. So as you can see from my introduction, the gravitational force is extremely important, and as I said already, one of the fundamental forces in nature. Now let's look at the properties of the gravitational force. The gravitational attraction depends on the amount of stuff an object is made of. Or in other words, the gravitational force depends on the mass of an object. Earth has lots of mass and produces a large attraction. The gravitational force of Earth is pretty significant for us. The force is always attractive and never repulsive. Gravitation is the tendency for bodies to attract each other. And so Newton realized this attraction was responsible for maintaining the orbits of celestial bodies. And he was able to write his law of gravitation, defining the strength of this attractive force between particles. As I already said, the gravitational force is universal, and it's everywhere in the universe. Even 2 molecules in air attract each other with a gravitational force that is not zero. Even though this force is extremely small, it is there. Our bodies attract gravitationally the air molecules around us. So for example, the gravitational force between an apple and the Earth is 0.8 newtons. And this is a pretty significant force, having in mind that we're dealing with a small object such as an apple. But the size of this force comes from the fact that the Earth is giant. The size of Earth is extremely big compared to the size of an apple. Another example for the gravitational force between two objects would be the gravitational force between two people of average size. And this is less than 1 micronewton. As you can see, this force is very small. And of course, the reason for that is that for the average person, the mass of a body is very small compared to, in the previous example, the mass of Earth and the apple. However, this force is not zero. So the formula for the gravitational force magnitude is given by Newton's law of gravitation. The gravitational force F is equal to the product of a constant g, which is known as the gravitational constant, and has a value of 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. And the product of the mass of the first object, the mass of the second object, divided by the distance between those two objects to the second power. So again, the gravitational force F is equal to the product of the gravitational constant, the mass of object 1, the mass of object 2, and it's inversely proportional to the distance between the two objects to the second power. The force always points from one particle to the other, so this equation can be written in a vector form like so. Here are my two objects, let's say small spheres with mass m1 and m2, and for now let's consider those to be point particles. These two spheres are a distance r from each other. Let's also consider a coordinate system with origin O, and so both of those two particles are located along the single axis of this coordinate system, which I'm going to label with R. So this is a radial coordinate system which has a center at the origin, and then the positive direction is outward along a straight line, like that. So then, the gravitational force between the two particles points like so. So this is the gravitational force that particle 1 experiences due to the interaction with particle 2. So I can call it F1. And then, of course, on the other hand, particle M2 also experiences gravitational force F2, which is directed towards M1 because it's due to particle M1. Since this gravitational force, by definition, from the previous slide, is the product of the gravitational constant, the masses of the two particles, and inversely proportional to the distance squared, we see that the two forces F1 and F2 must be equal to each other. Indeed, the gravitational force between two objects is a force that each of the objects experiences. It is not split into two parts based on what the masses of the two objects are. No, both objects experience the same gravitational force. So in terms of my notation here with the radial coordinate system, the gravitational force can be written in vector form as F is equal to G, M1, M2 divided by R squared. R hat, where R hat is the unit vector in this radial coordinate system. So Newton's law of gravitation was defined for small particles. However, this law can be applied for objects that have actual physical dimensions, as long as the distance between the two objects is much larger than their sizes. So, for example, the Moon and the Earth are very large celestial bodies. However, the distance between the two is large enough for them to be essentially point particles, and therefore the gravitational force formula can be applied to them to calculate the force between them. The Earth and the Moon are far enough to consider them point particles and apply Newton's law of gravitation. But how about the previously mentioned example of the apple and Earth? From the point of view of the apple, the broad and level Earth stretching out to the horizon beneath the apple certainly doesn't look like a particle. However, Newton was able to solve the apple-Earth problem with the shell theorem. The shell theorem states that a uniform spherical shell of matter attracts a particle that is outside the shell as if all the shell's mass were concentrated at its center. According to the shell theorem, Earth can be thought of as a nest of shells, one within another, and each shell attracting a particle outside Earth's surface as if the mass of that shell were at the center of the shell. Thus, from the apple's point of view, Earth does behave like a particle, one that is located at the center of Earth and has a mass equal to that of Earth. So let's see exactly how this shell theorem works. So here is a shell, let's say one of the shells from which the Earth is made, but it can be any other spherical object, for simplicity of course. Here's our particle, and this particle has mass m. The shell will have mass capital M. So we know that the shell attracts this particle with a gravitational force F. But how can I calculate the force exerted by the entire shell? This is not very easy, and so let's take another approach. Let's divide this shell into small parts. Each of these parts will have the same mass. Let's call this mass m prime. So then each element with mass m prime, shade 1, will attract this mass with some force. And the force of attraction, let's call it F1 prime. Another element will attract this mass, let's say this element here, will attract this mass with a different force because it's a different distance from the mass. Let's call this force F2. And so on and so forth. So all the elements in this shell will be attracting this mass with a certain amount of force, which is based on the distance between the elements and that particle here. And when all of these are added together, the net force will be directed straight towards the center of the shell. Okay, so now if I focused all of the mass of the shell right at the center right here, it turns out, and this can be experimented with, it turns out that the shell will attract the particle with the exact same force. So imagine that this is the shell, or the mass of the shell focused at this point. The particle m is still the same distance from the center as before. the force that the particle will experience from the shell will be the same net force. Somebody might ask, what happens if the particle is placed inside the shell? Would the particle then experience gravitational force? And is it going to be the same as the previously calculated net force? Let's examine this situation. So here again I have my spherical shell. For simplicity, I'm going to place the particle at the center of the shell. So the particle has mass m, the shell has mass capital M. Again, I'm going to divide the shell into small pieces, each with mass m prime. And so on and so forth. Okay, so now let's look at the piece that I just filled in. This piece is going to attract this particle towards it with gravitational force F1. Okay, but then in the shell there is another piece that is diametrically positioned on the other side of particle M. So right here, it also has mass m prime. So this piece is going to exert the same force, F1, on the particle, but in the opposite direction. Remember, this particle is placed at the center of the shell. So the distance between the particle and this mass m prime and the distance between the particle and this mass m prime, they're equal. So that means that the gravitational force due to each part of the shell here and here is the same. So those two forces balance each other out. Well, that happens for all other pairs of diametrically positioned pieces of the shell. So as a result, the net force that acts on the particle when it's inside the shell is zero. The same result is achieved when the particle is located somewhere else, not on the center, because the forces that will act on the particle will all even out eventually to produce a zero net force. So the particle will be closer to a certain number of shells, a certain number of particles from the shell. So it's going to experience high attractive forces towards that region of the shell, but the majority of the particles will be further away and they will be causing a gravitational pull away from the shell region with the closer particles, and so that will result in zero net gravitational force. So the shell theorem is totally applicable for particles that are outside of the shell, and for particles that are inside of the shell, the result of the shell theorem is that the net gravitational force is zero. Another effect of the difference in size between an apple and the Earth in terms of gravitational force is the acceleration with which those objects are moving. We know that if we have an apple above ground and let go, it's going to fall towards ground with the gravitational acceleration, which is 9.8 meters per second squared. Contrary to the obvious or quote-unquote fact that the Earth is not moving, the Earth is actually moving with some acceleration. This acceleration is extremely small, of the order of 10 to the negative 25th meters per second squared, simply because the Earth is so massive. So the apple is not very massive, therefore the acceleration with which it moves is obviously measurable. The acceleration of the Earth is extremely small, and that is because the Earth is so massive. From our previous discussions on forces, we know that forces obey the principle of superposition. So the gravitational force obeys this principle of superposition as well. If we have a system of particles, the the net gravitational force on any one of those particles can be calculated as the sum of gravitational forces that each of the other particles in the system exerts on that particle. Consider, for example, a system of 5 particles, and I want to calculate the net gravitational force that particle 1 experiences. So particle 1 is under the action of force F12 due to particle 2, and also force F13 due to particle 3, force F14 due to particle 4, and force F15 due to particle 5. So to find the net force, I simply need to calculate the vector sum of those 4 forces. So F1 net is simply equal to F12 plus F13 plus F14 plus F15. Of course, the addition of these forces must be done by components, as always, in order to find the magnitude of the net force on particle 1. So the same, of course, principle applies for the gravitational force that any other particle in this system is experiencing. This net force, F1 net, can also be written as the sum of F1I, where I varies from 2 to n, and so n can be any number depending on the number of particles. If we are considering an actual real extended object, then the net force is the sum of infinitely large number of individual gravitational forces. In order to deal with that type of a problem, we transition the sum here to an integral, like so. And as already stated before, if the object is a uniform sphere or shell, we can treat its mass as being at its center instead. In other words, we can consider this sphere or shell a point particle. I want to discuss now gravitation near Earth's surface and some interesting effects or examples that follow from that. So we know from before that the gravitational force was calculated as the mass of an object times the gravitational acceleration. So to write it in the formalism of gravitation, let's rename the gravitational acceleration with A sub g. Okay, so on one hand, the gravitational force is equal to the mass of an object times the gravitational acceleration, but on another hand, from Newton's definition, the gravitational force is equal to the gravitational constant times the mass of Earth times the mass of the object divided by the distance between the object and the center of the Earth to the second power. So comparing those two and eliminating the mass gives us an expression for the gravitational acceleration. So the gravitational acceleration is equal to the gravitational constant times the mass of Earth divided by the distance from the object to the center of the Earth to the second power. So this gives us a formula that we can use to calculate the value of the gravitational acceleration at different distances from the center of the Earth. Here in this table, there are several different values for the gravitational acceleration given as a function of the distance from the Earth. So, the gravitational acceleration at the surface of the Earth is 9.83 meters per second squared. On Mount Everest, which is 8.8 kilometers from the surface of the Earth, the gravitational acceleration is 9.8 meters per second squared. At the orbit of the space shuttle, which is about 400 kilometers above the surface of the Earth, the gravitational acceleration is 8.7 meters per second squared. And a distance from the Earth where communication satellites are positioned, which is 35,700 kilometers, the gravitational acceleration is 0.225 meters per second squared. As you can see, and we know that the gravitational acceleration decreases the further away we get from the Earth. The calculated gravitational acceleration, AG, will differ slightly from the measured value, G, at any location. For that reason, the calculated gravitational force on an object will not match its weight for three reasons. First is that the Earth's mass is not uniformly distributed. Here you can see the plot of density versus distance from the center of the Earth. And as you can see, the value changes the further away we get from the center of the Earth, and this is due to the fact that inside the Earth we have several different layers made from different materials with different densities. And so when we calculate the gravitational acceleration, we use the average density, but that's why we get the average value. In reality, different different points of the Earth, the gravitational acceleration will have slightly different value because the thickness of the layers underneath is different depending on where you are on Earth. Therefore, the density will be varying differently, and therefore the result will be changing. Another reason why the gravitational force would not match the weight of an object is that the Earth is not a sphere. The Earth is more like a ellipsoid. So I will attempt to draw it. Of course, this is extremely exaggerated. It is not that squished, but you can think of the Earth as being something like that. And therefore, the values for the gravitational acceleration at the poles will be larger than the values of the gravitational acceleration on the equator. And then, the third reason is that the Earth rotates as well. So the rotation gives a rise of a centripetal acceleration for an object that is on the surface of the Earth anywhere except the points that pass through the axis of rotation, of course, which are the poles. So the existence of centripetal acceleration then means that there is a centripetal force that acts on the object, and so that is going to change the value of the gravitational force that the object experiences. So let's see an illustration of this statement. Here is a crate that is placed on some scales, and the scales are laying on the surface of the Earth. Since the Earth rotates about the axis that passes through the two poles, then the scale also rotates. And so, for this crate, the free body diagram will look like so. We have the normal force up, away from the surface, and then we have the gravitational force pulling straight down towards the center of the Earth. So the crate is in circular motion, and I must note that this is uniform circular motion around the axis that passes through the poles of the Earth. Therefore, it experiences centripetal force. So this centripetal force is the result of the difference between the normal force and the gravitational force that act on the crate. On the other hand, this is equal to mass times the radial acceleration of this crate. And the radial acceleration is related to the angular velocity of Earth as omega squared times the radius of Earth. The minus sign here appears due to the fact that the radial acceleration is directed in opposite direction to the positive orientation of the radial axis, as discussed when I talked about the gravitational force definition. So then, from the scale, we read the weight of the crate, and that would be equal to the normal force. So Fn is equal to mg. So then substituting here and moving this term on the right-hand side of the equation and cancelling out all the masses, I end up with an expression for the gravitational acceleration g. The gravitational acceleration g will be equal to the free fall acceleration, will be equal to the gravitational acceleration ag minus the centripetal acceleration. So you can see how these two have the same value, only for points that do not rotate about the Earth. So that would be the North and South poles. And for any other point of Earth, the acceleration of free fall will be less than the actual gravitational acceleration by that term. The shell theorem also means that a uniform shell of matter exerts no net gravitational force on a particle located inside of it. I already discussed this option, and I explained how the net force acting on a particle inside a spherical shell is formed, and that this net force is equal to 0. This, however, can be used to find the gravitational force inside a uniform density Earth, and for that I'm going to use the following example. Here is the Earth. Let's imagine that there is a shaft that connects 2 points along the diameter of the Earth, one on each side of the Earth. Let's drop an object to fall in that shaft. So initially the object is above the surface. It's going to get attracted by the entire mass of the Earth. Now once the object starts to fall inside the shaft, the mass that is above it, so the mass of the shell that is above it, no longer exerts gravitational force on this mass. Only the mass of Earth that is below the object exerts gravitational force on the object. Let's call the mass of that part of Earth that is below the object m inside. Then the object experiences gravitational force F, which is equal to the gravitational constant times the mass of this object times the mass of the inside of Earth divided by the distance to the center to the second power. Since the density of Earth is considered here to be constant, I can use the expression for density to relate the mass inside with the total mass of Earth. So the density is equal to the mass inside divided by 4/3 pi r to the third power, which is the volume of a sphere with radius r. But the density of Earth, of course, is also equal to the mass of Earth divided by 4/3 pi r to the third power, where r here is the radius of Earth. So now if I substitute m ins right here, I get an expression for the force that the small mass m experiences in terms of the mass of the entire Earth and the radius of the Earth, and the distance from the center that looks like so. So the force that the object experiences under the surface of the Earth is equal to the gravitational constant times the mass of the object times the mass of the entire Earth divided by the radius of the Earth to the third power times the distance from this object to the center of the Earth. Here what I did is, from the above relationship, I expressed m ins in terms of the mass of Earth, substituted in the previous formula here, and got this result. Let's note some interesting facts that follow from this form of the force that the object experiences. First of all, the force is proportional linearly to the distance from the center of the Earth. And also, the force decreases as the object gets closer to the center of the Earth, and it is zero at the center of the Earth. Once the object passes the center of the Earth, then it starts to slow down, as now under the object there is more mass that is pulling it in the opposite direction. So once the object reaches the surface of the Earth on the other side, here, it will be at rest. And then due to gravitational pull from Earth, it's going to start to fall, slows down. It's going to start to fall and it accelerates. When it reaches this point, no net force acts on it because it's at the center of the Earth. It passes this point, and now force directed in the opposite direction starts to act on it, slows it down until it stops right here, and then goes the other way, like so. Essentially, it will oscillate back and forth between the 2 points on the surface of the Earth. So in this sense, I can also rewrite the gravitational force formula for this particular situation to look like so, where K is equal to all of these constants, and then the minus sign represents the fact that the force and the direction of the radial axis are opposite to each other. Essentially, this is a form of the Hooke's law that we discussed for a mass attached to a spring. But here, this is for the gravitational force. Let's now talk about gravitational potential energy. The gravitational potential energy is a property of a pair of particles. We cannot divide it up to say how much of it belongs to each particle in the pair. We often speak of the gravitational potential energy of a baseball in the ball-earth system. We get away with this because the energy change appears almost entirely as kinetic energy of the ball. But this is only true for systems where one object is much less massive than the other. So here is my system of two particles, one with mass m and one with mass capital M. These two particles are separated by a distance r. Since we are calculating potential energy, we need to choose a reference configuration where the gravitational potential energy of this system of particles is equal to 0. Well, the most intuitive selection would be when those two particles are infinitely apart from each other. So this distance here, if it approaches infinity, then the gravitational potential energy between these two particles will be 0. Why is that? Remember, the gravitational force between two objects is inversely proportional to the distance between the objects to the second power. So that means that if these two are infinitely apart from each other, the gravitational force essentially is 0. So therefore, the gravitational potential energy between the two will also be 0. So here is my selection. The gravitational potential energy of the system is 0 when the distance between the two particles is infinity, which then implies that for any finite distance between the particles, the gravitational potential energy is not a 0, but rather it's a negative number. The closer the two particles are to each other, the more negative the gravitational potential energy becomes. So this can be then summarized into the following expression for the gravitational potential energy of a system of two particles. The gravitational potential energy of the system is equal to minus the product of the gravitational constant, the mass of one of the particles, the mass of the other particle, divided by the distance between the two particles. For a system of particles, the gravitational potential energy will be simply the sum of several terms like this one for each pair of particles in the system. Here is an example with 3 particles, M1, M2, and M3, with the corresponding distances listed in the drawing here. So then the gravitational potential energy of that system of particles is simply the sum of the 3 terms that correspond to the gravitational potential energies of each pair of particles, taken with a minus sign at the end to match the definition of gravitational potential energy of a system of particles. From our discussion on gravitational potential energy in the module about energy, we know that the gravitational force is a conservative force. So the work done by this force does not depend on the path followed by the particles, only the difference in the initial and final positions of the particles. So, for example, if I take a particle from point A to point G along this path, the work done by the gravitational force will be the same as taking the particle from point A to point G straight up like so. Why is that? Well, we know that the gravitational force only does work when the object is moving radially away or towards, of course, the Earth. In this case, the object is moving radially away from the Earth along the stretch AB, but between B and C, the object is moving along an arc, which is along which the gravitational force does no work. Remember, work is defined as F d cosine of theta. So here, F is the gravitational force, d is the distance to the center of the Earth, and theta is the angle between the gravitational force and that distance. But since this is an arc, it's a part of a circle, the distance from any point on the arc to the center of the Earth is the same. And on top of that, the position vector and the force vector, the position vector and the force vector are at 180 degrees. I must make a correction here. So the force vector is pointing down towards the center of the Earth. That's the gravitational force. The displacement is along the arc here. So the angle between the gravitational force and the displacement, again, the force this way, the displacement that way, is 90 degrees. So this cosine here gives us a 0. So the gravitational force does no work along this stretch of the path. Then, again, the gravitational force does non-zero work from C to D. It does 0 work from D to E, non-zero work from E to F, and then again 0 work from F to G. So if I added all the works over all the stretches of the path, only the works done here, here, and here will be non-zero. Well, now imagine if I shrunk these arcs here, and essentially C overlaps with B, D overlaps with E and comes over here, F overlaps with G. So then that means that the particle will be displacing from A to G along this straight line. So the work done by the gravitational force will be still the same as the work done when the path was this one right here. So, since work done by the gravitational force is independent on the path, the gravitational potential energy change, delta U, is equal to the negative of the work done by the gravitational force. Let's now discuss several important points related to gravitational potential energy. So first, Newton's law of gravitation can be derived from the potential energy formula by taking the derivative. Remember from our previous discussions on gravitational potential energy that if we know the potential energy function as a function of position, if if I take the negative of the derivative with respect to position, that's going to give me the force that acts on this particular particle as a function of position. Well, I can do the same calculation in the framework of gravitational force. So the gravitational force will be equal to minus du dr, which is equal to minus d dr of negative g m over r. When you calculate this derivative, that is equal to minus g m over r squared. Since we always write this expression for the gravitational force for the smaller mass m, this minus simply represents the fact that the coordinate system of choice is selected so that the larger body m is the origin, and then we have the radial axis r pointing outward, and so then the small mass m experiences the gravitational force directed towards the larger mass, and so this minus reflects this result. The second point I want to discuss is escape speed. What is escape speed? Well, if you fire a projectile upward, for example, toss a ball straight upward, it will slow down, stop momentarily, and then return to the Earth. There is, however, a certain minimum initial speed that will cause a projectile to move upward forever, theoretically coming to rest only at infinity. So this minimum initial speed is called escape speed. So consider a projectile of mass m leaving the surface of a planet. So it could be Earth, it could be any other planet, with its escape speed v. The projectile has kinetic energy k, which is given by 1/2 mv squared, and potential energy u, which is given by minus g m times m divided by r. The condition is that this projectile will have zero kinetic energy and zero gravitational potential energy at infinity, at infinitely large distance from that planet. So the sum of those two energies is zero. Well, from here I can solve for v and get an expression for the escape speed for that planet. And so the escape speed v is equal to square root of 2 times g times the mass of the planet divided by the radius of the planet. So this applies for any celestial body. So if we are calculating the escape speed for Earth, m here will be the mass of Earth, r will be the radius of Earth. If we are calculating the escape speed for Jupiter, then m is the mass of Jupiter, r is the radius of Jupiter. If we are calculating the escape speed for the Sun, m will be the mass of Sun, r the radius of Sun. If we are calculating the escape speed for the Milky Way galaxy, then this will be the mass of the galaxy, this will be the radius of the galaxy, and so on and so forth. Specifically for Earth, rockets launch eastward to take advantage of Earth's rotational speed to reach v more easily. Now we can talk about planetary motion and satellites and Kepler's laws. The motion of the planets as they seemingly wander against the background of the stars have been a puzzle since the dawn of history. The quote-unquote loop-the-loop motion of Mars, shown in the figure here, was particularly baffling for scientists, for astronomers. Johannes Kepler, after a lifetime of study, worked out the empirical laws that govern these motions. Tycho Brahe, the last of the great astronomers to make observations without the help of a telescope, completed the extensive data from which Kepler was able to derive the 3 laws of planetary motion that now bear Kepler's name. And later, Newton showed that his law of gravitation leads to Kepler's laws as well. So Kepler's laws were derived for planets orbiting around the Sun, but they apply equally for satellites orbiting planets. More specifically, satellites orbiting the Earth. Before I discuss Kepler's laws, let's refresh our knowledge about the geometry of an ellipse. So here is an ellipse. Let's look at the main parameters that define it. So first we have the distance from the center to the end of the horizontal axis here where it crosses the ellipse. So this distance, which we label with A, is called the semi-major axis of the ellipse. An ellipse has 2 focal points, F and F prime, which are symmetrically positioned along the long axis with respect to the center of the ellipse. If I label the center of the ellipse with O, then the distance from each focal point to the center of the ellipse, so FO equal to F prime O is equal to the product of the eccentricity of the ellipse and the semi-major axis A. So this distance right here is the eccentricity times the semi-major axis. So E is the eccentricity of the ellipse. The eccentricity E is a measure of how unround the ellipse is. So when the eccentricity is equal to 0, that brings the 2 focal points at the center of the ellipse, and then the ellipse becomes a circle. So when E is equal to 0, we have circle. When E is different than 0, a positive number, then the circle becomes an ellipse with 2 focal points, the semi-major axis, and the distance from each focal point to the center being the eccentricity of the ellipse times the semi-major axis. And I should also note that this distance here is also E times A. Okay, so now let's look at a planet orbiting around a star. For example, the Earth orbiting around the Sun. So the orbit of the Earth is an ellipse in shape. We have the 2 focal points of the ellipse. The Sun is located at one of the focal points. This is the semi-major axis. This is the Earth right now. The position around the Sun is given by this position vector r, which starts at the origin of the which starts at the position of the Sun. So this focal point of the ellipse. Okay, so based on the position of the Earth around the ellipse, we have 2 very important points. We have a point at which the Earth is the closest to the Sun, and this is called perihelion. So the distance from the Sun to the closest point where the Earth is around its orbit, RP, is called perihelion. And then we have the furthest point away from the Sun. So the distance from the Sun to that furthest point is called aphelion. So RA, the largest distance from the Sun to the Earth, is called aphelion. Alright, so Kepler's first law, also known as the law of orbits, states that all planets move in elliptical orbits with the Sun at the focus. So the orbit is defined by its semi-major axis A and its eccentricity E. As I already mentioned, an eccentricity of 0 corresponds to a circle. The eccentricity of Earth's orbit is 0.0167. So that means that it is not a very pronounced ellipse, but it's not a circle at all. Kepler's second law is the law of areas. A line that connects a planet to the Sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is, the rate, the ADT, at which it sweeps out area A is constant. And this statement is equivalent to the law of conservation of angular momentum. Quantitatively, the second law just tells us that the planet will move most slowly when it's farthest from the Sun and most rapidly when it's nearest to the Sun. The area of the shaded wedge closely approximates the area swept out in time delta t by a line connecting the Sun and the planet, which are separated by a distance r. The area delta A of the wedge is approximately the area of a triangle with base r times delta theta and height r. So the area of this shaded region here, delta A, is approximately 1/2 r squared times delta theta. Now notice that this is an approximated result. And this is because this area delta A is pretty large actually. So if I want to get an exact result, I must decrease the time interval. So I want to set delta t to approach 0. So that is the same as taking a time derivative of the area. So this then becomes dA dt is equal to 1/2 r squared d theta dt, but that's nothing more than 1/2 r squared times omega, which is the angular speed of the line connecting the Sun and the planet as the line rotates around the Sun. Now let's look at the momentum of the planet as it rotates around the Sun. So the linear momentum of the planet is presented here with its perpendicular and radial components. So I can calculate the angular momentum of the planet, L, which we know that from the definition of angular momentum, this is r times p perpendicular. So this is r times mv perpendicular. And if I replace v perpendicular with its equal in terms of the radius of the or the distance from the Sun to the planet and the angular velocity, this becomes r times m omega r. Or in other words, this is m r squared omega. Well, in the expression I have for the change in area with time, I have r squared omega. From the angular momentum, I have r squared omega. So then that means that the dA dt is equal to L divided by 2m. If the dA dt is constant, as Kepler said it is, that means the angular momentum L must also be constant. Or in other words, the angular momentum is conserved. And so Kepler's second law is equivalent to the law of conservation of angular momentum. So if dA dt is constant, then it follows that L is conserved. Or in other words, L is constant as well. Finally, Kepler's third law, known also as the law of periods, states that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So t squared, the period of any planet to the second power, is proportional to the cube of the semi-major axis of the orbit. So for an elliptical orbit, we will replace r with the value of the semi-major axis a. And of course, for a circular orbit, then that will be the radius of the orbit. Notice that this law here, the mass dependence is only the mass of the central body about which the planet orbits. It is independent on the mass of the planet. So then if this is applied to a satellite, the period here depends only on the mass of, let's say, Earth, and it doesn't depend on the mass of the satellite. Let's now discuss satellites, and more specifically orbits and energy. As a satellite orbits Earth in an elliptical path, both its speed, which fixes its kinetic energy k, and its distance from the center of Earth, which fixes its gravitational potential energy u, fluctuate with fixed periods. However, the mechanical energy E of the satellite remains constant. Furthermore, since the satellite's mass is so much smaller than Earth's mass, we assign U and E for the Earth satellite system to the satellite alone. So we assign the gravitational potential energy and the mechanical energy of the Earth satellite system to the satellite alone. Consider the following setup. Here is the Earth, here is the satellite, it orbits around the Earth. The distance between the satellite and the Earth is r. Then the gravitational force between the Earth and the satellite should be equal to the centripetal force that acts on the satellite. From here, G, mass of Earth times mass of the satellite divided by the distance between the two, is equal to the mass of the satellite times the speed squared. If I divide both by 2, then I found an expression of the kinetic energy in terms of the mass of Earth, mass of satellite, and the distance between the two. So the kinetic energy of the satellite is simply equal to Gm over 2 times r. But now let's remember what the gravitational potential energy of a system of two particles is equal to. From the definition, this is minus Gm divided by r. So if you compare those two, you will see that K is equal to minus the gravitational potential energy of the Earth satellite system divided by 2. So then the total mechanical energy E is equal to the kinetic energy plus the gravitational potential energy, or this is equal to G m divided by 2 times r minus G m divided by r. And so this leads to minus G m divided by 2 times r. Or, in other words, the mechanical energy of the satellite is equal to minus the kinetic energy of the satellite. And this is for a circular orbit. So again, for a circular orbit, the mechanical energy is equal to minus Gm divided by 2r. What about elliptical orbit? Well, simply replace r with the semi-major axis. So E is equal to minus Gm divided by 2 times a. This is for elliptical orbit. And with this, I'm concluding the lecture on gravitation.